So let's move into this new section. Now we're starting to talk about differentiation techniques. Remember in a previous lecture, we talked about differentiating using the limit of the difference quotient, right? Okay, so let's look at a notation that we did speak about in that lecture, but let's look at it in this particular section. F prime of x, that's how you read that little tick mark, prime. F prime of x means the derivative of x with respect to y. Now you're like, how come y? Because y and f of x represent the same thing. Remember, f of x took the place of y when we realized the equation became a function, right? So, because y and f of x represent the same thing, an equation. Now, here's another notation for f prime of x. So f prime of x can be written as dy over dx. And you're like, what does that mean? The derivative of y with respect to x. The derivative of y with respect to x. Or f prime of x can be written as the derivative of f of x with respect to x. All right? So, all three of these notations mean the same thing. So please understand that. By the way, I've got another notation for you. F prime of 2. Remember, in that other lecture, we did talk about doing that. And that meant to take the derivative, or plug in the 2 to the derivative of f of x, right? All right, here's another notation, another way they could write this. The derivative of y with respect to x, because that's what f of x, f prime of x means. But now, right, it's at 2. So the derivative of y with respect to x evaluated at x equals 2. Good? Okay. Now, if you remember that last lecture where we took the limits of the difference quotient, which was also basically finding the slope of a tangent line by taking that limit of the difference quotient, if we do that often enough, patterns start to develop. For instance, if my function is x squared, and I take the limit of the difference quotient to find the derivative of x squared, I'm going to notice that every single time the derivative of that function is going to be 2x. If I take the function x to the third, and I take the derivative of it using the limit of the difference quotient, I'm going to find that the derivative is always going to be 3x squared. And the same thing, if my function is x to the power of 4, I'm going to find that the derivative, using that limit of the difference quotient, is going to be 4x to the third. By looking at this, x squared, x to the third, x to the fourth, even x to the fifth, x to the sixth, I see a pattern actually starts to develop. Once I see the pattern, then I can actually start finalizing, so to speak. I can start actually bringing about some different differentiation techniques, some rules, if you will. So stay tuned. I got some of those. Okay, so based on those last 3 examples that I gave us, which I rewrote here, the first theorem, known as the power rule, actually develops. This helps us to take the derivative of x to a power. So let's look at the theorem. For any real number k, so that means fractions, decimals, negatives, okay? If y equals x to the k, then the derivative of y with respect to x. Another way to write that is the derivative of x to the k with respect to x is equal to. Now, let's take a look at what we did in just a couple of minutes ago. If we had looked at the limit of the difference quotient with respect to all of these functions, x to the second, x to the third, x to the fourth, we would have gotten these answers. Now there's a pattern that's developing. Do you notice that this 2 is now in the front? This power of 3 also came to the front. This power of 4 also came to the front. Do you notice the new power here is a 1? Well, isn't that 1 less than 2? And the new power here is a 2. Well, that's 1 less than 3. And the power here is a 3. That's 1 less than 4, isn't it? So the derivative of x to a power actually becomes, I bring the exponent down and I multiply it to the original function, and then I take the power and I subtract by 1. Cool? Okay. Again, when you take the derivative of x to a power, the exponent comes down in front, it gets multiplied to the equation, and reduce the original power by 1. So let's look at some examples. How about y equals x to the power of 8? If I want to take the derivative of this, the derivative of y with respect to x, here's the original function. What's the first thing I'm going to do based upon this theorem? Correct. I am going to take my power and I am going to bring it down in front. So I am going to take this 8 and I am going to bring it down in front and multiply it. And then I subtract 1 from it. Which means in this particular case, my derivative becomes 8x to the power of 7. That would be the derivative of y with respect to x. Cool? Okay, got another one for us. How about if we have x to the power of 10? If I want to take the derivative of this function, this y, with respect to x, here's the original function. What do I do first? Good. I take the power and I bring it down in front, multiplied, and then I subtract 1 because that's what this power rule tells us, which means my derivative of y with respect to x becomes 10x to the power of 9. Cool? Got another one. What happens if my y is now equal to 1 over x to the power of 6? And you're like, wait a minute. This power rule isn't talking about when x is in the denominator. You're right, it isn't. So I need to come up with another way to write 1 over x to the power of 6. I need this x to the power of 6 to be in the numerator. But I can't just arbitrarily move it from the denominator to the numerator unless I put a negative in front of that exponent. Because now that negative says this whole thing was originally in the denominator, wasn't it? Okay, so if I am taking the derivative of y with respect to x, I am taking it of the function x to the negative 6. So what's the first thing we do? Good, we take the exponent and we bring it down in front and multiply, and then, subtract 1. Which means, in this particular case, the derivative of y with respect to x is equal to negative 6 times x to the negative 7. And if they don't want a negative exponent, that means you have to remember to bring the x back to the denominator, and the power becomes a positive 7. Cool? Okay. What happens if they give me, my equation is just 5. It could be 10, it could be negative 3. What happens if they give me that and they say, find the derivative? You're like, where's the x? That's a good question. Where is the x? 5 times x to the power of what? Yeah, 0. Because x to the 0 power is just 1, isn't it? So isn't this the same thing as just 5? Good. So if I took the derivative of y with respect to x of this particular function, 5x to the 0, we would get, what would you do? Good. You bring the exponent down in front and multiplied, and then you'd subtract by 1, wouldn't you? Well, let's see. 0 times anything is just what? Yeah, it's 0. I don't care about the exponent being now x to the negative 1 because I'm going to multiply the whole thing by 0. What happens if this was a 3? This would be 3 times x to the power of 0, wouldn't it? Same thing, 0 in front. I would still get 0. What if this was a negative 10? This would be negative 10 times x to the 0. 0 would come in front. I'd still get a 0, wouldn't I? Okay, so here's what happens based upon example number 4. I end up with this particular theorem, theorem number 2. And theorem number 2 states the derivative of a constant, isn't 5 a constant? If this was negative 3, I would still get a 0, wouldn't I? Because, bring the 0 down, right? If this was a 10, same thing, I'd still get a 0, wouldn't I? So the derivative of a constant is always, what do you think? Always 0. That's theorem number 2. The derivative of a constant is always 0. The derivative with respect to x of c, which is a constant, is going to always be equal to 0. Cool? Okay, hang in there. Got another one for us. So let's look at problem number 5. We're still differentiating. So, based upon that theorem that we just worked with, in order for us to take the derivative of f of x, right? You're like, wait, what am I doing with that 3? Hold on to that 3 a second. So if I was just working with x to the 7th, what would you do first? Good, you'd bring down the 7 times x to the power of 7 minus 1. Good, that's what you would do, right? Because that's what that theorem told us. Now, here's the deal. In this case, I have 3 times that function, don't I? Well, what do you think you're going to do with the 3 here? Yeah, very good. You're going to do 3 times that whole thing, right? Does that make sense? Okay, so since it makes sense, that means the derivative is going to be 21 x to the power of 6. That's right, because the 3 is multiplied to the whole thing, right? Okay, so let's look here on problem number 6. If they want me to take the derivative of this, and it's the x to the 20th, we're going to bring down that 20 multiplied by x to the power of 20 minus 1. Agreed? Well, good. Now, what do you think you're going to do with the negative 5? Yeah, since this whole thing was multiplied by negative 5, that means this part is also going to get multiplied by negative 5, which means we end up with the derivative being negative 100 x to the power of 19. Does that make sense? Good. Problem number 7, you getting the hang of this? Then let's see if you follow along. So on problem 19, the derivative of f of x is going to be negative 4.8 times 1/3 x to the power of 1/3 minus 1. Okay, so negative 4.8 times 1/3. I know some of you guys have your calculators out. What'd you get? Good. Negative 1.6 x to the power of, That's right, negative 2/3. That's a third minus 1. I sure hope you didn't use your calculator to figure out negative 2/3. By the way, if they don't want any negative exponents, this can be written as negative 1.6 over x to the positive 2/3. Cool? Okay. Problem number 8. You're like, wait, there's a square root. That's right, there's a square root. So here's the thing. Give me another way of writing the square root of x. This would be x. I'll give you a hint. It's a power. X to the what? That's right, 1 over 2. X is to the power of 1, and it's a square root, which means f of x is actually x to the 1/2 power. Cool? Yeah, got to remember these little things back from whenever we learned them in algebra days. Which means the derivative, that's right, 8 times 1/2 x to the 1/2 minus 1. Or 4x to the negative 1/2. And if they don't want any negative exponents, whoops, that is a small little 1. There we go. Agreed? Okay. All of this work actually alludes to theorem number 3. And I actually didn't want to put theorem number 3 up until right now. Why? Because if you understand what is going on here, that I'm doing 3 times this, then it was kind of like a common sense approach to you. You're like, well, of course I would multiply by 3 and negative 5 and negative 4.8 and 8. So theorem 3 basically says the derivative of a constant times a function is, here's what it looks like. The derivative with respect to x of a constant multiplied by a function is the exact same thing as if we took the constant and multiplied it by the derivative of the function, which is exactly what you did in these 4 problems. Good? Okay, stay tuned. Got another one. Let's look at this 4th theorem. This 4th theorem is known as the sum and difference rule. And it's saying if you take the derivative with respect to x of this sum, f of x plus g of x, it's the same as if I took the derivative of f of x, then the derivative of g of x, and then added them together. Almost like we're able to distribute this derivative part. By the way, it doesn't just work for addition, it also works if there's subtraction between these. Got it? Okay, so let's look at this first problem. They're asking me to take the derivative of this polynomial. And you're like, well, that's right. Well, I've got 3 things, added and subtracted together. And according to this theorem, I don't have to look at them all as one unit. I can look at them as 3 separate units, which is exactly what we're going to do. If they want me to take the derivative of this polynomial, then I'm going to look at it in 3 pieces. Why? Because this theorem says I can do that. I can actually take the derivative with respect to x of the 5x squared, and then subtract from it the derivative with respect to x of 7x, and then add to it the derivative with respect to x of 3. I can look at it in 3 pieces, which is going to make our lives so much simpler. With me? Okay, so let's see what you got. I need to take the derivative of 5x squared. So let's see what you remember from the last few problems. Yeah, that power of 2 is going to come down. X gets raised to the 2 minus 1, right? And then we multiply by this 5. Agreed? Minus This x is to the power of 1 technically. So I bring down the 1, and I take x to the 1 minus 0, right? And then this 7 gets multiplied. Agreed? And lastly, we're going to add, I'm taking the derivative of a constant. Go back to that problem number 4 we did towards the beginning of this lecture. What's the derivative of a constant? Good, it's 0. That was theorem number 2. Cool? Okay, so let's go back. What do we end up with here? Good, 10x to the power of 1 minus 7x. Whoops, I made a mistake here. Did you catch that? I think you did. I just didn't hear you, sorry. 1 minus 1, right? You're supposed to subtract 1 from the exponent. So 7x to the power of 0 plus 0, so I don't have to worry about that. So 10x minus, what's x to the power of 0? Yeah, just 1. So this is basically 7 times 1, which means we have 10x minus 7. Good? Okay. Let's do another example. Let's look at our function being the cubed root of x plus 4 over the square root of x. And yes, I know I'm pushing you a little bit, but you know, you can handle it. Because here's the thing. Except for this one, right? Even theorem number 3. The first theorem basically tells me I need an x to a power. And as long as I have an x to a power, I know how to take the derivative. If you notice, theorems 3 and 4 didn't really tell me how to take the derivative of a new function. Theorems 3 and 4 basically said, this is how you take the derivative if the functions are added or subtracted together, or if there's a constant in front. Notice, theorem number 1, the power theorem, x to the k, this is the only one that literally is telling me how to take the derivative of a function. Which means every time I get a function, my goal is to rewrite these or have them written as x to a power. So that's the cubed root of x. How do you write that? Forgetting the cubed root or not writing it with the cubed root sign, how do you write that? Yeah, that's x to the power of 1, which makes this x to the 1/3. Good. How about this other one? 4 over x to the power of what? Yeah, 1/2, because that's a 1 and that's a square root. But again, the denominator is the issue. So how do I get that x to the 1/2 from the denominator to the numerator? Good, some of you remembered that other example we did. What was it, example number 3? It becomes 4x to the negative 1/2. Excellent. And now that we actually have our function in a power format, now I can take the derivative, which means I am going to take the derivative of x to the 1/3 and add to it the derivative of 4x to the negative 1/2. Yes? Okay, see if you follow along. What am I going to do here? Good, bring down the 1/3, x to the power of, good, 1/3 minus 1. Excellent. Add to it, what do we do with that 4? Excellent, just write it down because that's what that third theorem told us. Just write down the constant. And now I'm doing the derivative of x to the negative 1/2. So what do? Good, bring down the power, x to the original power minus 1. Awesome, you guys are doing great. Okay, so 1/3 x to the negative 2/3 plus, oh yeah, that's not a plus, is it? Why? Because you're doing 4 times a negative half. What does that give you? Good, that gives you a negative 1/2 x to the negative 3/2. Hopefully you didn't have to use your calculator on that. Good with this? Good. But if they tell us to rewrite this with no negative exponents, you have to remember that these are going to go all in the denominator. So this answer is going to look quite interesting, but it's all those algebraic rules of exponents that we did somewhere back in whatever algebra class it was. So x to the negative 2/3, 1 over 3x to the positive 2/3, minus 1 over 2x to the positive 3/2. If they don't want negative exponents, that's how I'm going to write it. Good? Good. If you need to, rewind it and look at this problem again. And while you do that, I am going to be back with some more examples. So stay tuned. All right, let's look at this third example. It's asking us to find the derivative of the function at 10, right? So remember, there's another way of writing this. They could have actually written it as the derivative of y with respect to x evaluated at x equals 10. Okay. They say to find the derivative of the function at x equals 10 if the function is x squared plus 4x minus 5. So, in order to find the derivative of the function at 10, what do you think you've got to do first? Yeah, first you actually have to find the derivative. So first find the derivative of the function, right? Okay, so we are taking the derivative of x squared plus 4x minus 5, which means, yep, we can take the derivative of each one individually, which is going to make our lives much nicer. All right, so follow along. What do we do here? Good, bring the 2 down. Subtract 1 from the exponent, so you just get 2x, don't you? Okay. On the second part, good, this is 4 times the 1, because you bring the 1 down. And now it becomes x to the power of 0, because you're going to do 1 minus 1, aren't you? And the derivative of a constant? Yeah, that's just 0, so I'm not even going to bother writing it. So we end up with 2x plus 4, don't we? For the derivative, this is actually the derivative of the function is 2x plus 4. Agreed? Good. But they didn't ask for the derivative of the function. They wanted the derivative of the function at 10. So now what do you think you're going to do? Excellent. You're going to plug it in. You're right. You plug in the 10 to the derivative. Why? Because it said f prime of 10. We needed the derivative first so I could plug the 10 in. Not before. So that gives me a 24. Do you agree? Good. Let's look at this one. Find the equation of a tangent line to the graph of f of x at the point 4, 14. Now we did one of these in a previous lecture, but before I get to that, hold on. We did one of these in a previous lecture. In order to find the equation of a line, you need to know what 2 pieces of information. Yeah, you need to know the slope and you need to know the point. Well, you've got a point, but do you know the slope? Nope. What do you have to do to find the slope? Yeah, this is where the previous lecture came in. Remember in the previous lecture, when you took the limit of the difference quotient, that was the derivative, wasn't it? But it was also the slope of a tangent line. In the previous lecture, when you took the limit of the difference quotient, that was actually finding the derivative. but that was also the definition of the slope of a tangent line. So first things first, in this particular case, for us to find the slope first, we need to find the derivative. So first things first, we need to find slope. And to find the slope, that means we need to find the derivative of the function. When I know the derivative of the function, I can find the slope. Cool? Okay. Gratefully, in this section, finding the derivative is a whole lot easier than it was in that previous lecture. Because that previous lecture, I had to do the difference quotient, then find the limit. That was kind of long. Hopefully this one won't be so bad. So to find the derivative of the function, we're going to take the derivative of x squared minus the derivative of, okay, I ain't leaving it as a square root of x. How do you write it? Good. X to the power of 1/2. Okay, so I'm going to give you a moment. You find me the derivative of x squared. Good, I heard some of you. You're like, bring the 2 down, minus 1, 2x. Excellent. The derivative of x to the 1/2. Give you a moment. You find it. Good. That's 1/2 x to the negative 1/2. Because you had to minus 1 from that, didn't you, to find the derivative? Excellent. Okay, so now I'm going to simplify a little bit. 2x minus negative exponent, isn't it? So that's 1 over 2 times the square root of x. Agreed? Okay. So now, this is your generic slope equation. Remember that? This is the generic slope equation. I need the slope of this function at this point. This point is made up of an x and a y, isn't it? Gratefully, I have an x because this says the derivative of the function at x. So to find the specific function, remember, this is the generic slope. To find the specific slope, we got to do f prime of, yeah, my x is a 4. So I'm going to plug in 4 here. So we got 2 times 4, right? Minus 1 over 2 times the square root of 4. Agreed? All right. 8 minus 1 over, looks like 2 times 2. So the derivative of this x is 8 minus a quarter. Stay off the calculators. What's 8 minus a quarter? All right. Some of you are on your calculators anyway. But some of you didn't get on your calculators and you still found 31 over 4. Yay! So I just found the slope. That's my slope. This is the slope. M equals 31 over 4. Right? Okay. Need a little bit of board space. So you found the slope. Do you have a point? Yes, we have a point. The point was 4, 14, right? So since I have a slope, and since I have the point, can I now find the equation of the line? You're right, I sure can find the equation of the line. And in order to find the equation of the line, I need my point-slope form. Cool? Okay, remember, the slope is 31 over 4. The point is 414. And if you need to write it down over here to help yourself out, then please by all means do so. And now we're simply going to plug this information into the point slope form. So tell me what to write. Y minus, good, 14, because that's the y, equals m, which is 31 over 4, times x minus 4. Excellent. Good job. Okay, so you guys are remembering how to find the equations of lines. Those 4's drop, right? Bring the 14 over. 31 over 4x minus 17. Good? Yes, in this section, finding the slope is a lot easier than it was in the previous section. Why? Because I don't have to deal with the difference quotient. I can just use theorem number 1, which helps me find the derivative of powers. Okay, stay tuned. I got another problem similar. Let's look at this 5th problem. It asks us to find the points on the graph at which the tangent line is horizontal. And it says if none exists, then state that. Now notice what it's asking you. They're asking you to find the points. They're asking you to find an x and a y. This is what we're looking for. Remember the last problem? It actually gave me the point 4, 14. This problem is asking me to find that point at which the tangent line is horizontal. Horizontal is this line, isn't it? If you remember the graph of a horizontal line, that means it passes through the y-axis only. Agreed? It's a flat line, isn't it? Okay, so let's just say this was 4, which means your line here would be y equals 4, wouldn't it? What's the slope of that line? Do you remember? Yeah, some of you do, some of you don't. Remember Kansas, prairie land, right? Flat, just like that, flat. Do you have any hills? 0 hills on prairie land. This horizontal line has a slope of 0, doesn't it? If they're saying the tangent line is horizontal, that means the tangent line slope is m equals 0. And how do I find the slope of a tangent line? That's right, you got to take the derivative. This implies then that the derivative of the function must be equal to 0, because that is how you find the slope of a tangent line, by the derivative. Good? Horizontal lines have a slope of 0. That means my tangent line has a slope of 0. And to find the slope of a tangent line, you've got to take the derivative, which means the derivative must be equal to 0. So, first things first, that means I need the derivative of this function. So, the derivative of the function is going to be us taking the derivative of each of these individually. And I'm hoping you follow along. So, the derivative of this function is going to be the first one. Bring down the 3, so what's 1/3 times 3? Well, let me just write it. You would end up with 1/3 times 3 times x to the second, wouldn't you? Plus, oh, I forgot the 1/2. Whoops. 1/2 times 2 times x to the first. Yep, and that's just going to go to 0, isn't it? So I don't worry about that because it's just a constant. Okay. So what's the derivative? X squared plus x. All right. And we said, because the tangent line is horizontal, that the derivative is 0, which means that x squared plus x must equal 0. This is how you're going to find the x's in your point. This is how you find those x's. Cool? Okay. Well, I'm going to bring this up over here because I have a little bit of factoring to do, don't I? Like, why factoring? Well, it's a second degree equation, right? Okay, so what's the first step of factoring? Good. Factor out what's in common. I see an x in common. I am pulling out an x. I set them each equal to 0. And I solve. So I have x equals 0 and x equals -1. So how many points do I have? Yep, 2 points. Okay, so now hang in there. You just found your x. I need to find the y. How do you think you're going to find the y value when you know your x's? You're like, I'm not sure. What does f of x stand for? It stands for y. Remember that. F of x stands for y. This is another way of saying y. So, to find the y's, we have to use the original function, because the original function is the y. Got it? Are you with me? Okay, so my first x is 0. If I find f of 0, what do I end up with when I plug 0 into here? Yeah, you end up with -2. So one of my points is 0, -2. Your other x value was a -1, which means you need to find f of -1. What happens when you plug the -1 into here? Yeah, you get -1/3 plus 1/2 minus 2, right? And then you're going to have to get the common denominator of 6. And I'm going to let you do that work. And for me, when I did this, I got -11/6. Hopefully we agree. Which means my second point is -1 comma -11/6. So in this particular case, there are 2 points that will make my tangent line, or pardon me, there are 2 points where my tangent line for this graph is horizontal. All right? If you need to rewind this example, rewind this example. Please, rewind it. And in the meantime, I'm going to be back with some applications, more applications.